Welcome back to the Deep Dive. Today, we are doing something that, frankly, I think we should have done a long, long time ago.
Oh, yeah. What's that?
We're doing a gap analysis. But, and this is the key, not on a piece of software
Yeah.
and not on a market segment.
Okay, I'm intrigued.
We're doing a gap analysis on you.
On the listener. Wow. That feels a little aggressive for a Tuesday, doesn't it?
It is bold, I know. But stick with me here. I was looking through a lot of our listener feedback, the kinds of articles people are sending us, and I realized something. If you are listening to this show, you're probably pretty dangerous when it comes to AI. I mean, you know what RE is, retrieval augmented generation.
That's table stakes now.
You've probably built a bot that can talk to a PDF. You know what an agent is.
Yeah.
You definitely know you need guardrails so your chatbot doesn't, start reciting poetry about world domination.
Right. You've got the AI engineer starter pack.
Exactly. You have the AI engineer toolkit down cold.
Okay, so I see where you're going with this. You're talking about what I call the prototype plateau.
The prototype plateau. I like that.
Yeah, it's that point where you can serve a model. You can hook it up to a vector database, like, say, Pinecone or Weaviate. You can probably hack together a really, really impressive demo over a single weekend.
Exactly. The demo works. You show it to the team, the investors clap, but then
the real world hits.
Then you have to scale it. You have to pay for it. You have to make sure it doesn't break the law. And that right there is where we found this fascinating stack of documentation, this analysis that suggests there's a massive chasm, a huge gap between a competent AI engineer and a true AI architect.
There are missing chapters, so to speak.
Yes, missing chapters in the standard playbook that everyone's reading.
It's the difference between being a mechanic who can fix a car
and
being the civil engineer who designs the entire highway system, writes the fuel efficiency standards for the country, and manages the traffic flow for a whole city.
That is the perfect analogy. Absolutely perfect. The source material we're diving into today, it frames this whole thing as a gap analysis. And it argues that while most guides, most tutorials, they cover serving models, just getting an output, they completely, utterly miss the complex reality of creating, adapting, and this is the big one, affording them.
Affording them is the silent killer. It really is.
Tell me about that.
I mean, it is remarkably easy to build a system that is technically brilliant.
Yeah.
And at the same time, economically suicidal. I've seen it happen. I've seen startups burn through their entire seed round in like 3 months just because they didn't understand the economics of inference.
They just saw the cloud bill and had a heart attack.
Very much.
So our mission today, right here, is to bridge that gap. We're going to try to take you from engineer to architect by unpacking six missing pillars. These are the things that don't usually show up in those how to build a chatbot in 10 minutes medium articles.
Right. This is the stuff that happens after the demo. We've grouped them into 6 layers, sort of like a stack.
What are they?
So first you have the creation layer, then the cost layer, then what the notes call the iron. That's the hardware.
I love that. The iron.
Then you've got the fuel, which is data, the test, so deployment, and finally, the law, ethics and compliance.
The iron and the law. That sounds like a gritty HBO drama series.
Honestly, it can feel that dramatic sometimes. When you're the architect, the stakes are they're exponentially higher. You aren't just debugging a piece of code anymore.
You're managing enterprise-level risk.
Exactly. You're managing risk. Financial risk, legal risk, reputational risk. It's a whole different ballgame.
Okay, let's do this. Let's unpack it. We're starting at the very beginning, or maybe the re-beginning. Pillar number 1. The creation layer. The notes call this model adaptation.
Right. And this requires a really huge mental shift from where most people start.
How so?
Well, most people, especially when they're new to this, they operate in what I call the consumer mode.
Consumer?
Yeah, they think, okay, I'll just go download a Model Llama 3, Mistral, whatever is on top of the leaderboard this week, and I'll just use it.
Right. Or even simpler, just hit the OpenAI API, send a prompt, get some tokens back, job done.
Exactly. But an architect asks a fundamentally different question. They don't just ask, what model can I use? They ask, is this generic off-the-shelf model actually solving my specific, unique problem in the best possible way?
Because a foundation model, an FM, it's a generalist by definition.
Precisely. It knows a little bit about everything. It can write a poem. It can explain quantum physics. It can write Python code. But does it know your company's internal acronyms? Does it know the specific arcane formatting rules for a German legal contract?
Almost certainly not. So the engineer's first instinct is, let's use RAG.
Yeah.
Just shove all that context into the prompt.
And a RAG is great. I want to be very clear. Don't get me wrong. A RAG is a fantastic tool for knowledge retrieval. But it's not always the right tool for behavior modification or for deep stylistic changes. If you want the model to fundamentally think differently or speak in a very specific corporate voice, stuffing the prompt gets clunky and expensive.
So you need to go deeper.
You need to move beyond that simple staging to prod mentality and start talking about actually changing the model's brain.
So we are talking about fine-tuning, but wait a minute, I thought fine-tuning was sort of falling out of favor. Isn't it incredibly expensive and complicated?
That's the nuance, and that's the missing chapter. The source material points out that old-school fine-tuning, the way we used to do it, meant retraining the entire model.
The whole thing.
The whole thing. If you have a 70 billion parameter model and you wanted to fine-tune it, you used to have to calculate updates for all 70 billion of those parameters.
Which means, I mean, you need a massive cluster of GPUs just to hold all the optimizer states and gradients.
Yep.
You're basically trying to redo the work of Meta or Google in your own little data center.
Exactly. It's painfully slow, it's obscenely expensive, and it introduces a massive, massive risk that has a fantastic name.
What is it?
Catastrophic forgetting.
That sounds like a heavy metal band.
Yeah.
Or a Michael Bay movie.
It feels like it when it happens. It's what happens when you teach the model your new specific data, let's say, a bunch of medical records, and in the process, it completely forgets how to speak coherent English.
No way.
Oh, yeah. Or it loses its ability to do basic reasoning. You've essentially overwritten its general intelligence with your very specific niche noise.
So you've created a hyper-specialized idiot savant.
That's a great way to put it.
So the missing chapter here, the architect solution, is something called PEFT. PEFT.
Parameter efficient fine-tuning. PEFT is, and I don't think this is an exaggeration, it's the savior of the modern AI stack.
I see that acronym everywhere now. It's all over Twitter, all every paper. But let's actually break down why it works. How on earth do you fine-tune a model without touching most of the model? It sounds like a magic trick.
It feels like one, but it's just very clever math. Think of it this way. Imagine the base model, your Llama 3, is a massive, beautifully printed, leather-bound encyclopedia.
Okay.
Traditional fine-tuning is like taking a big red pen and physically rewriting entire pages of that encyclopedia just to add a new chapter on your company's HR policy.
You'd ruin the book,
Yeah.
and it would take forever.
It'll ruin the book. And you can never use the original pristine book again. You're stuck with your scribbled-on version.
Inefficient.
Totally. PEFT, on the other hand, is like sticking a clear, transparent overlay sheet on top of each page, a transparency.
Oh, like in an old school projector.
Exactly like that. You aren't touching the original text at all. The encyclopedia remains pristine. You are just writing your new notes on the overlay. So when you look through the overlay, you see the original knowledge plus your new notes, all combined.
That's a fantastic visual. And technically, the tool everyone is using for this specific trick is LoRA, right? L-O-R-A.
Yes. LoRA, which stands for low rank adaptation. It's the most popular PFT method. And it relies on a really, really cool mathematical insight called rank decomposition.
Okay, you might be losing me here.
Stick with me. It's not as bad as it sounds. It turns out that when you want to teach a big model a new task or a new style, the actual change required in its neural pathways is low rank.
Meaning simple.
In a way, yeah. It means you don't need a huge, high-dimensional, complex matrix of numbers to represent that change. The idea of the change is mathematically simple.
So you don't need to update a billion numbers to represent the change. You might only need a few thousand.
That is exactly it. So instead of updating a giant, say, 10,000 by 10,000 weight matrix in the model, LoRA freezes that big matrix. It doesn't touch it.
Okay.
And then it injects two new, very skinny matrices next to it, like a 10,000 by 8 matrix and an 8 by 10,000 matrix. You only train those tiny little slivers of new parameters.
And because they're tiny, the amount of memory you need just drops off a cliff.
We're talking a 90% reduction in VRAM sometimes. It's a game changer. It means you can fine-tune a massive 70 billion parameter model on a single high-end consumer GPU or a much cheaper cloud instance.
And what's QLoRA? I see that one too. Is that just the fancier version?
It's just the quantized version of that same idea. It takes the big base model, the encyclopedia, and it compresses it down to 4-bit precision to save even more memory.
Wow.
And then it trains the normal LoRA adapter, the transparency, on top of that super compressed base. That's how you see people online tuning these enormous models on their gaming PCs at home. It's democratizing the whole process.
Okay, so technically, LoRaWAN saves us a ton of money and time during training. I get that. But from an architecture perspective, this opens up a completely different capability, right? The sources mentioned something called adapter management.
This right here is the operational superpower of PFF. This is what separates the engineer from the architect. If you use traditional old-school fine-tuning and you have, say, 10 different business units that need customized models, legal, HR, coding, customer support, marketing,
Yeah, that's a common scenario.
you end up with 10 full copies of the model. That is 10 massive files, maybe 140 gigabytes each. That's 10 separate servers you have to provision and pay for just to host them.
Incredibly expensive and a total mess to manage.
With LoRaWAN, you have one frozen base model loaded into memory, just one. And then you have 10 tiny LoRaWAN adapters, which are just small files. We're talking megabytes, not gigabytes.
Okay.
When a request comes in tagged for the HR department, your inference server just hot swaps the little HR adapter into the model's memory. It takes milliseconds. Then the next request comes in for legal, and it swaps in the legal adapter.
So it's like multi-tenancy for AI models.
That's exactly what it is. It's like having one video game console, and you're just instantly swapping the cartridges depending on who's playing. That is a core architectural decision that can save you literally thousands and thousands of dollars in hosting costs every single month.
That is just... It's so smart. Okay, so we've customized the model's knowledge with LoRa, but what about its behavior? The sources go on to mention alignment strategies. This feels different.
It is different. This is creation layer part 2. Knowledge is one thing, preference is another. How do you make the model behave the way you want it to? How do you stop it from being toxic or unhelpful? How do you ensure it answers in a perfect JSON format every single time, no exceptions?
This is the alignment problem. And the industry standard we always hear about is RLHF reinforcement, learning from human feedback. This is supposed to be the secret sauce behind ChatGPT, right?
Right. And for a long time, it was the only game in town if you were serious about alignment. But RLHF is incredibly complex. I mean, just think about the engineering pipeline you have to build.
Walk me through it.
Okay, first you have the main model. Then you have to use it to generate a bunch of different answers to the same prompt. Then you have to pay humans to sit there and rank them to say this one is better than that one.
The human feedback part.
Yes. Then you have to train a whole separate reward model to try and learn to mimic what the humans liked.
So a second model.
A second model. And then you use a really complex reinforcement learning algorithm called PPO proximal policy optimization to update your main model based on the scores from the reward model.
That sounds like a lot of moving parts, a lot of places for things to go wrong.
It's extremely fragile. PPO is notoriously unstable. People who train with it say it's like trying to balance a broom on your nose while riding a unicycle on a tightrope.
Wow.
If you get the hyperparameters just slightly wrong, the whole thing can collapse and your model starts speaking complete gibberish.
Okay, so it's powerful but dangerous. But the sources suggest there's a new player in town, something called DPO.
Direct preference optimization, yes. This was a massive breakthrough that came out of Stanford. They basically looked at the incredibly complicated math behind RLHF and said, wait a minute, I think we can simplify this a lot.
What was the insight?
They realized that the preference data itself, that simple A is better than B data from the human labelers, already directly defines the optimal policy. You don't actually need the separate reward model as a middleman.
You don't need the second model at all.
You don't need it. And you don't need PPO. You can just construct a clever loss function that directly tells the model, hey, the math for answer A should be more likely and the math for answer B should be less likely. You just push and pull directly on the model's probabilities.
So it completely cuts out the middleman.
It cuts out half the infrastructure and all of the instability. It's leaner, it's more stable, it's way more computationally cheap, and for many tasks, it gets the same or even better results.
Okay, then the obvious question for an architect is, why would anyone still use RLHF if DPO is so much better?
Well, a couple of reasons. First, RLHF is battle-tested. We know it works at the absolute mega scale of something like GPT-4. It's proven. DPO is newer. There's some debate about whether it scales quite as well for extremely complex multi-step reasoning tasks. So the architect has to make that trade-off decision.
Do we need the robust, expensive, complex, but proven RLHF?
Or do we go with the efficient, cheaper, simpler, and still emerging DPO for our specific use case?
It's trade-off. Architecture is always about trade-offs.
Always. There's no single right answer.
And speaking of trade-offs, let's talk about size. This feels like a big one. The final piece of this creation layer in our notes is model distillation. I feel like for the last 2 years, the entire trend was bigger is better, more parameters, a trillion parameters.
Yeah, with the parameter race.
And now the pendulum is swinging back hard. We're seeing a massive shift toward smarter is better, regardless of size. And that's where this teacher and student model concept comes in.
Explain that dynamic to me. Okay, let's say you have a really complex task you need a model to do.
Yeah.
But you have a constraint. You need it to run on an edge device like a phone, or you need the latency to be near instant, or you just need it to be super, super cheap to run.
You can't use GPT-4 for that.
Absolutely not. It's too big, it's too slow, and it requires an internet connection. It fails on all 3 counts.
So what do you do?
So you take GPT-4, the teacher model, and you use its powerful brain to generate, say, 50,000 perfect gold standard examples of how to solve your specific little task.
You're using the big model to synthesize a perfect textbook on one subject.
That's the perfect analogy. You create the textbook, then you take a tiny little model, what we're now calling a small language model, or SLM, maybe 2 or 3 billion parameters, and that's your student.
And you train the student on the textbook.
You train the student only on that textbook. The student learns to perfectly mimic the teacher's reasoning and output style, but only for that one specific domain.
So the student isn't a general-purpose genius like the teacher, but it becomes a world-class expert at that one thing you need it to do.
Precisely. And because it's tiny, it runs on a fraction of the hardware with barely any latency for a fraction of the cost. If all you need is a model to summarize your internal emails into 3 bullet points,
You don't need a trillion-parameter model that also knows how to write Shakespearean sonnets.
you absolutely do not. You distill that one specific capability into a small, efficient package.
Which is the most perfect segue possible to our second pillar. We've created the model, we've tuned it with LoRa, we've aligned it with DPO, we've distilled it down to size. Now, we have to run it, the cost layer.
Or, as the outline calls it, advanced inference optimization.
This is where the rubber meets the road.
Mm,
Or maybe where the wallet meets the cloud provider's billing department.
that's more like it.
I feel like inference cost is the thing that quietly kills most AI projects after the initial hype dies down.
It absolutely is. I can't even tell you how many times I've seen a team celebrate a successful launch. Everyone's popping champagne. And then a month later, they're in a panic room, scrambling to shut the whole thing down because their AWS bill is higher than their monthly revenue.
And the sources say this isn't just about picking a cheaper server. It's about, and I'm quoting, deep technical tactics.
It is. It really is. A regular engineer, they'll spin up a GPU instance and they'll just hit run. An architect optimizes the entire inference stack from top to bottom. You have to squeeze every last drop of performance out of that expensive piece of silicon.
Okay, so let's start with quantization again. We mentioned it briefly with QLoRa, but let's do a proper deep dive here because this feels controversial.
Huh.
I hear people say that quantization makes the model dumber.
It can. It absolutely can if you do it wrong or naively. Quantization is the art, and it is an art, of reducing the numerical precision of the model's weights.
Yep.
So computers usually do all this neural network math in formats like FP16 or BF16, that's 16-bit floating point numbers. They're pretty precise, but they take up a lot of memory and a lot of bandwidth to move around.
So we're trying to make the numbers simpler to save space.
Exactly. Think of it like image compression. You have a huge, raw TIFF file directly from a professional camera. It's gorgeous, but it's 50 megabytes.
Right.
You convert it to a high-quality JPEG. Now it's maybe 2 megabytes. To the human eye, can you tell the difference?
Usually not, no.
Exactly. But if you compress it too much, if you crank the JPEG quality down to 10%, you get ugly artifacts, gets all blocky and weird.
Right, I've seen that.
Quantization is the exact same principle for numbers. We're moving from those 16-bit numbers down to 8-bit integers, or even in some cases, FP4, 4-bit floating point.
4-bit. That seems impossibly low. You only have, what, 16 possible values you can represent for any given number? How can a complex model possibly think with that little precision?
This is where the specific algorithms mentioned in the source, things like AWQ and GPTQ, come in. They are absolutely brilliant. They had a key insight, which is that in a massive neural network, not all weights are created equal.
What do you mean by that?
Some neurons are just louder than others. They have huge activation values. They are the outliers. And it turns out they carry a disproportionate amount of the important semantic information. Other neurons are just kind of murmuring in the background. They contribute, but they aren't the stars of the show.
Okay, so there are VIP neurons.
There are VIPs. And algorithms like AWQ, which stands for Activation Aware Weight Quantization, they go through and identify these VIP neurons first. They say, okay, these important ones, we are going to keep these in a higher precision, or we'll apply a special scaling factor to them so their signal doesn't get crushed during the compression.
And the murmuring ones.
The murmuring neurons, we crush those down to 4-bit. We don't care as much about their precision.
So it's a selective, intelligent compression. It protects what's important.
Exactly. And by protecting those outliers, you can run a model in 4-bit with almost zero perceptible loss in performance on many benchmarks. But an architect needs to know more than that. They need to ask, okay, if I use AWQ, will it actually run on my specific deployment target? Does my inference server, like vLLM or TGI, actually support it?
So it's not just make it smaller. It's make it smaller in a way that is compatible with the rest of my stack.
100%. The ability to fit a 70 billion parameter model onto a single A100 GPU with 80 gigabytes of VRAM versus needing 2 of them? That decision instantly saves you 50% on your hosting bill. That is high-impact architecture.
Okay, that saves memory. That's a huge win. But what about speed? The actual user experience, the user sitting there watching that blinking cursor, waiting. Latency is the enemy.
That brings us to the next part of the stack, decoding strategies, and specifically to a really cool technique called speculative decoding.
I love the name. It sounds like the model's gambling.
In a way, it is. And to understand why this is so effective, you have to understand a key hardware limitation of modern GPUs when running LLMs.
What's that?
They are usually memory bandwidth bound, not compute bound.
Unpack that for me. What does that mean?
It means the bottleneck isn't the raw speed of doing the math. The GPU is incredibly fast at matrix multiplications. The real bottleneck is the time it takes to move the massive model weights, all those billions of parameters, from the physical VRAM chips over to the compute cores that do the math.
So it's like having a super fast reader who has to walk all the way across the library to the shelf to fish every single word.
Yeah.
One by one.
Perfect analogy. And because of that trip to the library, generating just one single token can take a surprisingly long time.
So how does speculative decoding cheat?
It cheats by using 2 models. You have your big, powerful, slow model, and then you have a tiny, fast draft model, like one of those student models we just talked about.
Okay.
When it's time to generate text, the little draft model instantly guesses the next, say, 3 or 4 words.
It just blurts them out.
It scribbles them down instantly because it's so small and fast, it has no memory bandwidth issue. Then, the big, slow, powerful model does its one slow trip to the library. But instead of generating one word, it just checks the work of the little model. It looks at the 4 words the draft model wrote and says, yes, that's correct. Yes, that's correct. No, that one is wrong. I'll fix it.
And checking is faster than generating from scratch.
Much, much faster, because you can check all 4 of those predicted tokens in parallel in a single forward pass. So if the draft model is right, and for simple, predictable parts of a sentence like, the cat sat on the field, it's usually right, you effectively get 3 or 4 tokens for the price of one slow memory fetch.
That is absolutely genius. You're directly optimizing for the known hardware bottleneck.
It can lead to a massive speed up in your user-facing tokens per second.
And then there's KV caching. The notes list that here too.
Key value caching. This isn't optional anymore. This is
Yeah.
mandatory. When you're having a long conversation with a chatbot, every time it generates a new word, the model effectively has to reread and reprocess the entire conversation history from the beginning.
That sounds exhausting and incredibly redundant.
It's a ton of redundant math. The KV cache is a special part of the GPU's memory where it saves the mathematical representation of the past conversation, the key and value states from the attention mechanism. So for the next token, the model only has to process the single new word and combine it with the cached history.
But that cache must take up a lot of memory itself
Right.
as the conversation gets longer.
A massive amount of memory. This is a huge gotcha. As the context window gets longer, the KV cache can actually become larger than the model weights themselves. It's a huge memory hog.
And that causes problems.
It causes big problems, which leads to a whole new generation of architectural solutions, like an algorithm called page attention, which is brilliant. It breaks the cache up into smaller virtual memory pages, so you don't run out of contiguous memory. It's just, it's layers upon layers of optimization.
Wow. Okay, one more topic on this cost layer. Batching.
Ah, yes, batching. This is the difference between running a taxi service and running a city bus service.
Go on, I like this.
Okay, so static batching the old way is like a city bus that has a really weird rule. It refuses to leave the bus stop until every single seat on the bus is full.
Okay, that's inefficient.
And worse, once it leaves, it won't let anyone off until everyone on the bus has reached their final destination.
That sounds awful.
In AI terms, it means if you send a batch of 10 user requests to the GPU, and one of them is asking for a really long 2,000-word essay, while the other 9 just want a simple yes-no answer.
The 9 yes-no people have to wait.
The GPU is completely locked up, chugging away on that essay, and the 9 other requests are just sitting there finished, but they can't be returned to the user. They're waiting for no reason.
So what's the architectural fix?
Continuous batching. It has other names too, like in-flight batching.
Sounds much more efficient.
It's completely dynamic. It's like having a fleet of Ubers instead of that weird bus. It treats every slot on the GPU independently. As soon as one of those yes-no requests is finished processing, that slot is instantly freed up, and a new request from the waiting queue jumps in, even while the long essay request is still chugging along in the other slots.
So the GPU is always as close to 100% utilized as possible. No wasted cycles.
Exactly. For any kind of high-throughput, user-facing application, continuous batching is absolutely non-negotiable. If your inference server isn't using it, you are literally just lighting money on fire.
All right, it's a powerful statement. We've covered the model and the cost. Now we need something to run all this optimized code on. Pillar 3, the iron, infrastructure and hardware selection.
The default cry of every engineer everywhere, I need more GPUs.
Right, and the architect's response is which ones and why? Because they are not all the same, not by a long shot.
Not at all. The source material lays this out as a compute decision matrix. And honestly, this is one of those areas where you can immediately tell who has actually deployed a real system to production and who has only ever worked in a research notebook.
Let's break down the main contenders. First, you have the beast, the undisputed king, the NVIDIA H100.
The H100 is the Ferrari of the AI world. It's an absolute marvel of engineering. It has the custom transformer engine for performance, massive memory bandwidth. If you are training a new model from scratch or doing a massive fine-tuning job on a huge model, you want H100s. Full stop.
But they are incredibly expensive and notoriously hard to get your hands on. There's a global shortage.
Extremely. And here's the dirty secret. For a lot of inference workloads, just serving the already trained model, they are often massive overkill.
It's like buying a Ferrari to deliver pizzas.
That's the perfect analogy. You can do it, sure, but your profit margins on those pizzas are going to be deeply, deeply negative.
So what's the right tool for the job? What's the pizza delivery scooter of the AI world?
According to these notes, and I agree with this, it's the NVIDIA L4.
The L4. I feel like nobody talks about this card. It doesn't get the headlines.
It's the unsung hero. It's a card that NVIDIA designed specifically for inference. It has 24 gigs of memory, which is enough for a lot of quantized models. It consumes very little power, and it's dramatically cheaper to rent in the cloud. You can stack a whole bunch of them in a server.
So for 90% of common business use cases like a chatbot or a RAG system or a classification model, the L4 is actually the smarter architectural choice.
In many, many cases, yes, it's the financially responsible choice.
And then there are the walled gardens, the specialized non-NVIDIA chips. AWS has Inferentia and Trainium. Google has their TPUs.
This is a major strategic bet for an architect. You have to understand why these chips exist. AWS and Google are building their own custom silicon because they are sick and tired of paying the NVIDIA tax.
They want to break the monopoly.
They want to control their own destiny and, more importantly, their own margins.
So if I'm an architect on AWS and I choose to use their Inferentia chip, it's cheaper.
Oh, much cheaper. On paper, the price performance can be 40 to 50% better than the equivalent NVIDIA GPU sometimes, but there is a trap.
Of course there's a trap. There's always a trap.
The trap is software. The entire world of AI runs on NVIDIA's software stack, which is called CUD. Every open source library, every GitHub repo, every tutorial on the internet just assumes you were using CUD. It's the universal language.
And Inferentia and TPUs don't use CUD.
They can't. They have their own proprietary software stacks. AWS has something called the Neuron SDK. Google has its own framework for TPUs, and they're getting better. But they are not as mature or as seamless as CUD.
So what does that mean in practice?
It means you might have to rewrite parts of your model's code to be compatible. You might hit a weird bug and find that there are literally 0 answers on Stack Overflow because only 10 other people on the planet are trying to do the exact same thing.
So the architect has to make a calculated risk. Is the engineering pain and the migration effort of moving to Inferentia worth the long-term cost savings?
That is the exact calculation. If your model is very stable and you're planning to run it at massive scale, 247 for the next 2 years without changing it, yes, the migration is probably worth it. If you're a startup that's iterating and changing your model every single week, stick with NVIDIA. The flexibility is worth the premium.
This really is a FinOps for AI mindset, financial operations.
It is, and it extends beyond just the chip choice to how you actually buy the compute time, too.
Yeah.
We have to talk about spot instances.
Ah, the bargain bin to the cloud, the ultimate high-risk, high-reward play.
Spot instances are the spare, unused server capacity that Amazon or Google or Microsoft sells off at a massive discount. We're talking 60, 70, sometimes 90% off the regular price.
But the catch is,
They can take it back from you with only a 2-minute warning. If someone else comes along and is willing to pay full price, your server just vanishes.
so you absolutely cannot run a production database on it,
Yeah.
and you probably shouldn't run a live customer-facing chatbot on it.
Correct. But for a long training run, or for a big batch processing job that can be interrupted,
It's perfect, because if the server dies, you just restart the job somewhere else.
only if you architect your system to handle that. This is key. An architect builds a training pipeline that automatically saves a checkpoint, a save file of the model's progress to persistent storage every 10 or 15 minutes.
Ah, okay.
If the spot instance gets killed, a simple script automatically detects the failure, requests a new spot instance, downloads the latest save file, and just resumes the training from where it left off.
So you get the Ferrari for the price of the scooter. You just have to accept that you might have a few unexpected pit stops along the way.
That's a perfect summary. And that is how you train state-of-the-art models on a startup's budget.
Okay, this is amazing. Moving on, we have the car, we have the engine, we've figured out the fuel efficiency. Wait, we need the actual fuel. Pillar 4, data strategy.
The fuel layer. And this is where almost all RG tutorials just completely fall apart. They assume you have a nice, clean, simple text file.
Right. The classic example is, here's a PDF of Moby Dick. Now you can ask questions about whales.
Yeah, exactly. But in a real enterprise, data is a nightmare. It's messy. It's siloed. It's in SQL databases. It's in PDFs. It's in unstructured text in emails. It's in weird proprietary mainframe formats from the 1980s. And most importantly, it is constantly changing every second of every day.
The sources here talk a lot about the data lakehouse. Is this just another marketing buzzword, or is it a real architectural pattern?
It's a real solution to a very specific and painful problem. The old way of doing this was ETL extract, transform, and load.
Right.
You would write a script to copy data from your real production database, you'd clean it up, and then you'd load it into a separate vector database for your AI application.
Okay, that seems logical.
But now you have 2 copies of the data, your system of record and your AI's copy. What happens when a customer updates their shipping address in the real database?
The AI's copy is now stale. It's out of date.
Exactly. So the AI hallucinates or just gives the user flat-out wrong information. And even worse, you potentially have a massive compliance and privacy nightmare on your hands.
The new architectural pattern, then, is zero-copy integration.
Yes. The goal is to connect the AI data pipelines directly to the source of truth, which is often a data lakehouse using open table formats like Apache Iceberg or Delta Lake.
So the AI is reading the data right where it lives, with no copying.
Exactly. If a record in the source table updates, the AI sees that change immediately on the next query. No stale data, no complicated synchronization scripts that break in the middle of the night. It's safer, it's simpler, and it's more compliant.
That feels much more robust.
Hmm.
Now, here's a really fascinating point from the notes that I wanted to dig into. Synthetic data generation.
This is becoming absolutely critical because sometimes you just don't have the data you need to train a model. Or even worse, the data you do have is radioactive.
Radioactive? What do you mean?
PII, personally identifiable information. Medical records, personal financial statements, classified government documents. You absolutely cannot train a model directly on that stuff without risking a massive career-ending privacy breach.
So what do? You have the data, but you can't use it.
You use a very powerful, trusted teacher model, like GPT-4, to generate fake data that looks and feels just like your real sensitive data, but contains no actual secrets.
Can you give me a concrete example?
Sure. Let's say you're a hospital and you want to build a model that can automatically extract symptoms and medications from a doctor's clinical notes. You can't show the model real patient notes.
Right, that would be a huge HIPAA violation.
So you write a careful prompt to a model like GPT-4 and you say, you are a medical data synthesizer. Create 1,000 fictional but realistic clinical notes for patients presenting with symptoms of type 2 diabetes. Use correct medical terminology, but ensure all patient names, dates, and locations are completely fake.
And GPT-4 effectively generates the curriculum for your student model.
Exactly. Then you take your smaller local model and you train it exclusively on that safe synthetic curriculum. Your model learns the structure of a clinical note. It learns how to identify terms like insulin or neuropathy. It learns the reasoning pattern without ever once seeing a real patient's private data.
That is genius. It's privacy-preserving machine learning.
It's becoming standard practice now in any high-security or highly regulated environment. It's also a great technique for dealing with imbalanced data. If you don't have enough examples of a rare event, you can just ask an LLM to generate more of them for you.
And to process all this data, synthetic or real, at scale, the sources call out two specific tools, Spark and Ray.
This is about feature engineering at scale. If you are trying to clean and process terabytes or petabytes of text data, a simple Python script running on your laptop is going to take 10 years to finish. You need distributed computing.
I know Spark. Apache Spark has been the king of big data for a decade. But what's Ray? I'm hearing that name more and more.
Ray is the up-and-comer that is built specifically for the AI and Python ecosystem. It's a framework that allows you to take your existing Python code like your data cleaning script, and with just a few small changes, instantly scale it out to run across a cluster of 100 machines. It handles all the messy parallelization stuff for you. An architect needs to be comfortable with these kinds of heavy-lifting industrial tools.
Okay, pillar 5. We're getting close to the end of the stack. Deployment. The notes call this the test.
Right. We've built the model. It's optimized for cost. We have a solid, scalable data pipeline now. We launch. We put it in front of users.
But how do we actually know if it's any good?
This is the online evaluation gap. Most teams, if they do any evaluation at all, they track things offline. They look at metrics like drift or their AGID triad.
Which are what, exactly?
They're useful but passive. It's like looking at your car's speedometer while you're driving. It tells you how fast you're going right now, but it doesn't tell you if you're about to drive off a cliff.
We need to be looking at the road ahead.
We need to be actively experimenting. We need to be running tests in production with real user traffic to see what actually works.
The outline here draws a distinction between A/B testing and something called multi-armed bandits. I know A/B testing. You split your traffic 50-50, right?
Right. 50% of your users get the old Model A, 50% get the new Model B. You let it run for a week, you look at the stats, and you see which one had a better click-through rate or whatever you're measuring.
Simple and straightforward.
But also incredibly wasteful. Think about it. What if your new Model B is actually terrible? It's buggy, it gives bad answers. You just subjected 50% of your entire user base to a terrible experience for a whole week.
Ouch. You've burned a lot of user trust just to get a statistic.
Exactly. So what's a better way? A multi-armed bandit.
That name comes from slot machines, right? The one-armed bandit.
Exactly. Imagine you're in a casino and there are 5 different slot machines in a row. You have a bucket of tokens and you want to win the most money possible. You need to figure out which of the 5 machines has the best payout.
Well, I'd probably put one token in each to start, just to see what happens.
Right. You explore. But as soon as you realize that machine #3 seems to be paying out more often than the others, you'd start putting most of your tokens in that one, right? You exploit your new knowledge.
But I'd still probably put a token in the other machines every once in a while, just in case they've warmed up.
That's the algorithm. In AI deployment, the bandit algorithm routes user traffic dynamically. It might start at 50-50, but if it starts seeing in real time that users are giving more thumbs-up ratings to the answers from Model A, it will automatically shift the traffic to 60-40, then 80-20, then 955 in favor of the better model.
So it automatically minimizes the regret, the number of users who are exposed to the worst-performing model.
Yes. It optimizes for user happiness and business metrics in real time. For many use cases, it's a much more sophisticated and efficient approach than a traditional A/B test.
And what about shadow mode? That sounds cautious.
This is for the truly risk-averse architect. And honestly, for any mission-critical system, everyone should start here. The idea is you deploy your new model to your production servers, but you don't show the user its answers.
Wait then, what's the point?
The user continues to interact with the old, stable, trusted model. That's what they see. But in the background, your new model also receives the exact same user query and generates an answer. You just log both answers to a database.
So you can compare them offline without any risk to the user.
Exactly. You can run a diff and see if the new model would have crashed or would have said something toxic or offensive. It's a flight simulator for your AI. You get to crash the plane in the simulator 100 times before you ever put real passengers on it.
And interleaving, what's that?
That's a technique that's really specific to search or recommendation systems. Instead of showing a user a page of results all from Model A or all from Model B, you mix them together. You interleave them.
Like shuffling two decks of cards together into one list.
Yes, the user just sees one unified list of results. If they click on result #1, which came from Model A, then Model A gets a point. If they click on result #2, which came from Model B, then B gets a point. It's a direct head-to-head taste test. It gives you a very clean, very powerful signal on which model is actually better at retrieving relevant information.
Amazing. Okay, we have arrived. The final pillar. The one that, let's be honest, usually gets ignored until the legal team sends a panicked all-caps email.
Pillar 6, responsible AI and compliance. The law.
The notes here are very clear to emphasize that this goes beyond security. We aren't just talking about prompt injection or protecting PII anymore. We are talking about ethics and a rapidly changing regulatory landscape.
This is the new frontier of system architecture. An architect 10 years ago just had to worry about uptime and latency. Now they have to worry about algorithmic bias metrics and EU regulations.
Well, let's start with that first one, bias detection. The notes mention a specific metric, demographic parity.
It's a statistical measure of fairness. The question it asks is, if your model is making decisions that affect people's lives, like approving loans or screening resumes for a job, does it approve them at the same rate across different demographic groups?
And if it doesn't, if it approves loans for one group at a 10% rate and another group at a 1% rate,
Then you have a biased model. And almost always, the bias doesn't come from a malicious algorithm. It comes from biased data that the algorithm learned from.
right. If your historical training data is 90% resumes from men who were hired, the model just learns a simple, dumb correlation that male-sounding traits are what lead to getting hired.
So as an architect, how do you fix it?
I imagine you have to intervene somehow.
You have to. You can try to rebalance the training data set. Maybe use that synthetic data technique we talked about to generate more examples of resumes for the underrepresented group. Or you can use a technique like RLHF to explicitly punish the model during training whenever it shows a biased preference.
But the first step is you have to measure it.
You have to measure it. If you don't have a dashboard that is actively tracking metrics like demographic parity or equalized odds, you are flying completely blind into a massive legal and ethical minefield.
And flying blind is rapidly becoming illegal. The regulatory landscape is shifting under our feet.
The EU AI is the big one that everyone is watching. It's a landmark piece of legislation. It categorizes all AI systems by their level of risk,
And if you're building a high-risk system,
which includes things like AI for employment, education, law enforcement, or critical infrastructure, the compliance requirements are going to be massive.
we are talking about mandatory conformity assessments, rigorous documentation of your data, requirements for human oversight, strict accuracy testing.
And absolutely massive fines if you screw it up. We are talking percentages of your company's global annual turnover. This isn't a slap on the wrist. This is an existential threat if you get it wrong.
So the architect's job now includes reading legislation and asking, is the chatbot I'm building to help with college applications considered a high-risk system under this act?
Yes, and they need to be familiar with frameworks like the NIST AI Risk Management Framework from the U.S. government, or international standards like ISO 42001. These are becoming the rule books that define what due diligence looks like for AI.
Finally, let's talk about the more immediate legal risks. The notes mention copyright and IP indemnification.
This is the super practical, what keeps the lawyers up at night side of this. If your coding assistant generates a chunk of code that looks exactly like a piece of copyrighted code from a competitor's proprietary code base, and your developer unknowingly ships that code in your product, who gets sued for copyright infringement?
You do. Your company does.
Exactly. But here's the architectural choice. Some of the big cloud providers are now offering indemnification.
Meaning they'll protect you.
Yes. Microsoft, Google, AWS, they now have legal clauses that say, if you use our foundation models and you get sued for copyright infringement based on their output, we will cover the legal costs. But only if you follow all their rules and use all their built-in safety guardrails.
That is a huge architectural detail that's buried in the terms of service.
It's a massive detail. It might completely determine which vendor you choose to build your entire company on. An architect reads the terms of service. They check if the model has copyright filters enabled that can detect when generated code strongly matches public GitHub repos.
It really does turn the architect into a bit of a lawyer.
Or at least it makes them the person who knows when to call the lawyer before it's too late.
Wow. We have covered a massive, massive amount of ground.
It's a journey, isn't it? From a single line of code to international law.
Let's just quickly recap the stack we built. It feels important to see it all together.
Okay, let's do it. We started at the very bottom, at the creation layer. We moved from just using generic models to truly adapting them with efficient tools like PFT and Lorai. We learned how to align their behavior with the more stable DPO. We realized we don't need to retrain the universe, just the delta.
Then we moved up to the cost layer. We learned to protect the important outlier neurons with AWQ quantization to shrink our models. We sped things up for the user with speculative decoding using little draft models, and we maximized our hardware utilization with continuous batching.
Then we built it on the iron. We stopped defaulting to the most expensive H100s and looked at the right tool for the job, like the L4 for inference. And we weighed the FinOps benefits of a custom chip like AWS Inferentia against the very real software cost of leaving the safety of the CUE ecosystem.
We fueled the whole thing with a modern data strategy. We implemented a lakehouse with zero-copy integration to keep our data fresh and compliant. And we used synthetic data generation as a powerful tool to train on secrets without ever revealing them.
Then we deployed it with active testing. We graduated from simple A/B testing to using multi-armed bandits to minimize user regret. And we used shadow mode as a Flink simulator to ensure safety and stability before a public launch.
And finally, we wrapped the entire stack in a layer of responsible AI. We set up dashboards to monitor for bias with metrics like demographic parity. We started preparing for the compliance burden of the EU AI Act. And we made a conscious choice about our vendor based on their IP indemnification clauses.
When you lay it all out like that, that is a massive toolkit.
It really truly highlights the gap we started this whole deep dive with.
It does. The source material we looked at, it ends with a really provocative question, a final thought. It asks us to consider the future of this very role.
Yes. Based on this huge shift we've just described, a shift toward FinOps, toward legal compliance, toward risk management, is the future AI architect more of a hands-on technical coder, or are they more of a strategic risk manager who just happens to understand technology?
That's a great question. What do you think?
I think the days of the lone wolf coder who can build and deploy these systems by themselves are ending, or they're already over.
Yeah.
The systems are just too powerful, too complex, and too consequential.
I agree completely. I think the AI architect is the bridge. They have to be the bridge. They're the only person in the organization who can fluently speak the language of the GPU and the language of the CFO. They have to understand tensor math and the liability cap in a contract. That is a powerful and very rare place to be.
It's a hybrid role for a new hybrid world.
Absolutely.
Well, listener, you have your work cut out for you. You have the map. You have the missing chapters.
Now, go build something amazing and then go optimize it.
Thanks for listening to The Deep Dive. We'll see you next time.